Today's lesson is about using vectors to describe forces. And yeah, I mean, it's sort of like the application or the purpose of one of the ways you can sort of apply what it is we've talked about. So many times these things will come up. This is a especially common one, right? When you're flying a plane. Not common for us, but I mean a common question. When you're flying the plane and you need to consider the direction of the wind. The wind may be working against you, it may be pushing you off course, it may be working for you. You need to think about that, right? Same thing in water, like with waves and so on. So sometimes like those kinds of questions we'll be getting into. And, this one, chains and tension and chords and things like that. So let's talk a little bit about vector components for a second. So it says two vectors that are perpendicular to each other and add to give the vector v are called rectangular components. So this is a really, really useful idea, and it kind of takes what we learned yesterday about addition and changes it into a different format. So for example, this vector I've just drawn, vector u, okay, in every way is equivalent to the sum of vector v plus vector w. Okay? So it's kind of like thinking, I could think of a single vector with an angle and a certain length, or I could think about two simpler vectors that meet at 90 degrees. It's kind of like what we did yesterday, but going in reverse, right? Yesterday we started with the idea of a person walking east and then walking north. Where would they end up? Today it's like a person walked northeast. What would be the equivalent if they had done just east and then just north? We know that v plus w, right? If I type v plus w, in every way it gives a vector that's the exact same as the original. So when you decompose a vector, or resolve it into its components, as we say, what you're doing is you're creating two perpendicular vectors, okay, that add up to make your original. And that can be really useful because perpendicular vectors have no influence on one another, right? No amount of v affects w, and no amount of w affects v. So it's not really, in one question it doesn't really matter, but if you're adding things together, it can really help. Anyway, let's look at it here for a second. So it says, draw the resultant for the rectangular components given, calculate the magnitude and direction relative to the horizontal vector. The sailboat's destination is 8 kilometers east, 6 kilometers north. Okay, so what's the resultant here, right? So if you draw this hypotenuse, you would see that 8 squared plus 6 squared equals whatever the magnitude of yours is. And the magnitude of yours, in this case, would be 10, right? So I'm going to ignore the vector signs. Please make sure that you do write them, but just for now, I'm going to say r squared, the resultant squared, would be the 8, the magnitude of the 8, squared plus the magnitude of the 6 squared. Now, I don't need to do the cosine law, right? The 2ab cos c, because cos c, c is 90 degrees, and cos of 90 is 0. So you don't really need this part if the things meet at 90 degrees. It's much simpler, right? You just do the typical Pythagorean theorem. Now it says calculate the magnitude and then the direction relative to the horizontal vector. So in other words, I would like to know the little angle that would go in this bottom left corner. And I could find that angle by doing inverse sine of 6 over 10, right? Because the resultant is 10 here. So let's just do that quickly. So it should be 8 and 6, right? So let's change vector v to be only 8 units over. Oh, I see. So change point D to be 8 units over, and change point E to be 6 units up. Okay, and we'll just get rid of this original one. Okay, so this is what we're looking at. You can see the length of vector A length of A is 10, right? That would be the magnitude of that vector, which we got using the Pythagorean theorem. And the angle would be inverse sine of length of W divided by length of A. And you get 36.87 degrees, which ought to be the same as when I measure the angle, right? 36.87 degrees. So we would say 36.87 degrees, and we'll say above the horizontal vector, or since this case it is sort of, we could just say east 36.87 degrees north, right? That would be a good way of giving that answer, because you start at east, we rotated 36.87 degrees towards north, and that's where we got the direction. Okay, another term to know is this term called the equilibrant. The only thing to know about the equilibrant is this statement down here. Simply that E plus R equals the zero vector, and therefore E is equal to the opposite of the equilibrium, of the resultant. So the equilibrant is like asking, if I introduced a force E into this equation, it would cancel out all other forces. So here in this case, you can see what's going on. F1 is pulling the object up, F2 is pulling the object up and to the right, and this is causing a resultant force up and to the right. If you introduced a down and to the left force at the same angle as R with the opposite magnitude of R, you would cancel the forces of F1 and F2. So F1 plus F2 equals R, and R plus E equals 0. E is, you kind of think of it as like the opposite of the answer. Whatever your answer is, the E is going in the opposite direction with the same magnitude. Or think of it this way: it's the same as the resultant, but with a negative sign at the front. Okay. Now, forces. So, force often is used in a. So here again, just the picture. If you have a force pulling up and a force pulling to the right, then you have a resultant force going this way. The equilibrant force would be going that way to cancel it out. Okay. Now, a object that is experiencing no net force. Okay, so let's write this another way. If an object is not accelerating, it is experiencing zero net force, and therefore all the forces that are acting on the object are balanced. Okay, so for example, you or me sitting in our chair, we're not accelerating. So the force that we are exerting downward, right, the force that gravity is pulling on us with, the floor or the chair is pushing up at you with the same amount of force, which is preventing you from accelerating in any direction. So if an object is not accelerating, it is experiencing zero net force. There are two ways this could happen. It could be at rest, or it could be moving at a constant speed. So it could be like sliding, or just moving but not accelerating. Okay. Okay, just to talk a little bit more about gravity. Every kilogram of mass, right? The Earth will exert 9.8 newtons per kilogram of force on that mass by gravity. Okay, so again, if you throw a ball up into the air, that gravitational force is going to accelerate it downward, and it will be experiencing a net force downward. But the same ball on the ground will be experiencing a net force downward, except that the ground is pushing up on the ball as well, right? The Earth is pulling it down, but the ground is pushing back up, and therefore the ball stays at rest. Okay, so weight is so this is the difference if you're not sure about this, between mass, okay, is the amount of stuff, and weight is the force that that stuff exerts on Earth. And that is why your weight changes if you were to go into space, but your mass does not. Your mass is simply what you're made of. Your weight is the actual force of that material. So, how much weight could you lift on Earth versus on the Moon? The mass, right, is not really the issue. It's the weight that's the issue. You could lift a great deal more mass on the Moon because the weight would be much lower. The force is lower, right? Okay, the process of finding the resultants, right. So often it is worth your time to take a force and express it as a horizontal force and a vertical force. So to do what we did at the beginning today, which is take your single vector and break it into two vectors. Again, this can be done quite easily. The horizontal force is the force times cos theta. The vertical force is the force times sine theta, where theta is the angle between the force and the horizontal. Okay? This picture kind of illustrates it. Again, why does it work this way? It's just trigonometry, right? If you take the hypotenuse and multiply by the cos of this angle, you would get the adjacent. If you multiplied by the sine of that angle, you would get the opposite, right? And the adjacent and the opposite are the two components of the force, the vertical and the horizontal. Of course, you got to be careful with your signs, depending on what you define as positive and negative. Let's try an example here. You'll see these really aren't too hard. They just you just got to make sure you can draw it and you understand what it's asking. So it says Jake is towing his friend on a toboggan using a rope. The rope makes an angle of 25 degrees with the horizontal. Jake is pulling with a force of 70 newtons. How much force is actually pulling the sled forward versus how much force is lifting the sled upward, right? Okay, so what I would suggest, let's draw this one quickly. So we want a vector that's 70 and we want it at an angle of 25 degrees. So let's see if we can do this. So okay, so I'm going to draw I'm going to do 70. I'm going to do a first vector which is 70 times cos 25, and it has 0. So this will be FH. Oops. Sorry. Okay, so vector. Okay, so there's the first vector. Okay, and let's just rename this to FH, and we can just get rid of that. Okay, so there's the horizontal force. You can see most of the force is exerted in a horizontal direction. It's not going to be more than 70, of course, because 70 is the full force that he's pulling with. The vertical force that he's pulling with is a vector that joins 0 to, where would this be? So 0 in the horizontal, and then 70 times sine 25 in the vertical. Okay, so that would be the vertical force that he's pulling with. Now again, the two forces have 90 degrees between them. We set it up that way. We wanted it that way, so that we resolved it into thinking about it as a vertical force and a horizontal force. When you add these two together, you would get the force that he's actually pulling with. Remember, when you add vectors together, you move FV. Either you complete the parallelogram, right, which would be my option here, or you move FV over to the other side so that you get to the end of this one and then you get to the end of the next one, and that will tell you where your destination is. Now, of course, when the vectors are perpendicular, it's not really even a parallelogram, it's actually just a rectangle. So that's not that hard in these questions. You just draw the rectangle and you just solve it. Let's check the length of U to make sure I did this right. So you can see U, the force here. I guess we could rename this to just F. The force has a magnitude of 70, and that 70 is made up of 63.4 newtons to the right and 29.58 newtons up. Okay, so 29.58 newtons are lifting the sled, or trying to lift the sled, and 63.4 newtons are pulling the sled horizontally. Okay, notice that the two components do not add up to the same number that the force did, right? Because they don't have that relationship. They have the relationship a squared plus b squared equals c squared. If I do that, plus 63.44 squared, I'm going to get a number that is very close to the square root of 70, or 70 squared, right? So this is a really good just one to go through. It's not hard, but it kind of helps you understand what the different things are doing here. So the sled is being pulled forward by a force of 63.44 newtons. And again, where do we get that from? Is 70 times cos of 25. And the sled is being lifted, or pulled upward, by a force of, what did we get there? 63.44 and 29.58 newtons. And again, how did I get that? Was I took the force, and this time I multiplied it by the sine of 25 instead of the cos. So again, not a difficult question to do, but just want to make sure you understand how it works and why it works this way. Okay? Again, you will get one like this or similar to this, that just to make sure we've got the basics. But of course, we're going to go to places a little more difficult than that. Okay, find the resultant and the equilibrant of two forces of 40 newtons and 20 newtons acting at an angle of 45 to one another. Okay, so what I want to do here is I want to demonstrate the vector addition applet that you have. There's a link to this on the front page of the website. So one force is 40 and one force is 20. So my A and B cap out at 10. So I'm going to set one to be 2, okay, and one to be 4. And I'll just remember that my final answer, I just need to multiply by 10, because instead of 20 and 40, I've got 2 and 4. Now the other thing I know is that these two forces act with 45 degrees to one another. So what I'm going to do here is I'm going to change the bearing of B so that this angle is 45 degrees. Okay? So this is what you've got. Now, if you're drawing this yourself, probably easier to actually have B be flat and have A come at 45 degrees so that the angle between them is still 45, right? It's probably easier to draw that way. So let's draw it that way, and you can just kind of keep it. The question is asking for the resultant. So the resultant, I just did it for you. If you go to show R, and show P is just finishing the parallelogram to remind you how to draw this. We don't really need that right now. I guess we can keep it on. So here's the resultant, and here's how to calculate it. Okay, I want to know the magnitude of A plus B. I do the cosine law, right, where the angle between the two, so the cosine law, remember, I'm not using 45 degrees. Because look, 45 degrees is not actually part of my question. It's over here in the corner, right? The angle I want is the angle down here. And you can see where I got that. I did 180 minus the theta. So I'm going to be using an angle of 135 here. That's what actually is going to go into my cosine law. When I do that, I solve that the vector is 5.596 newtons. So in our case, of course, we would go 55.96 newtons is going to be our answer. I have to multiply it by 10, right? Because in my question, I'm only working with 2 and 4 instead of 20 and 40. Now the bearing. My applet here will always tell you the angle from a straight north. So what it's telling you is that from straight north, your resultant is 75.36 degrees away. What it asks for, so it's not, that part may not be so useful. So let's maybe walk it back to, what if the whole thing was vertical again? So again, here's the two vectors separated by 45 degrees, except this time my bearing vector thing will just make a little bit more sense. So once again, The resultant is still the same because the angle between the vectors is still the same, and the vectors themselves are the same as what we had before. The bearing has changed because the bearing is always defaulting to counting from straight up. So the little angle in here from the purple to the green dashed line would be 30.61 degrees. So what I'm going to say is at an angle of 30.61 degrees from the 20 Newton force towards the 40 Newton force. Okay, and again, I'm not too concerned with how you describe this as long as you had a clear picture or were able to, articulate to me in whatever way that you're referring to the little angle in between the purple and the green dashed line. Okay, again, it's towards vector B, it's towards the 40 Newton force, not away from it, like over on this side. Okay, so that's our answer for that one. Again, how to do that one, the applet kind of shows you, but you're going to be doing a cosine law. So let's remind ourselves, cosine law to find magnitude. And then remember, the angle needed is not 45 degrees. 45 degrees is the angle that the two vectors make when they're tail to tail. But the cosine law, which would be the triangle, this triangle that I'm working on, for example, I would need this angle here, right? Once I got that angle, I would use the sine law to, the sine law to get the other angle over here, and I would just find out what that was, right? So you can look at an example of how to do that from the end yesterday. Okay, now these block questions are kind of tricky, so let's take a minute to try and make sure we understand this one. I don't think these ones up above are too hard. You just, they're just practicing your cosine law or your Pythagorean theorem. Just make sure, again, you do some examples and you pose any questions. The last two questions are not like that. There's a tension question, which is a very common, like, thinking style question to get, or application. And then there's this ramp. And both of these are often given because, as you can see, that's kind of it for today. I mean, there's a couple more examples from the book you can try, but for the lesson, it's really just these two. So let's make sure we have a good command of these two. To begin, let's try to draw the object on the ramp and discuss, what's happening to it. So the first thing I'm going to do is I'm going to draw the ramp. So I know that to have a 30-degree ramp, let's say we could draw a. So here's going to be my ramp. Let's say I believe as long as I make it twice as long as it is tall, it should have 30 degrees because that's sine 30 is 1/2, right? So just check the measurements. Am I wrong? Sine 30? No, so I guess I just didn't put these in the right place. Oh, sorry, it's hypotenuse has to be. No, wait a minute. Yeah, sorry, I'm thinking of the hypotenuse. So what I actually need here is a circle from A, that's 30, and then I need my triangle to end right there. No. Sorry, not right there. It needs to end. Sorry, it's just got to go right there. It has to have a height of 15. Not the best way of doing that, but anyway, it works. I hope it works. So let's drag point C, and point B is the same x-coordinate as D, but a y-coordinate of 0. Okay, so now we have a 30-degree ramp. Okay, sorry, I just remade it so it's actually accurate here. Okay, so finally, I have myself a triangle with a 30-degree incline. So here's the ramp. Okay. Now my object is simply sitting on this ramp. So you could draw like a little box or something. We'll just draw a little box. Okay. So I have a little box, and the box is resting on this not cooperating. Okay. A little box, it's resting on the ramp. Okay. And it's what we need to do here is figure out sort of like, let's figure out what we're trying to do. It says a 10-kilogram block is resting on a ramp that's inclined at an angle of 30. What force parallel to the ramp would prevent the block from moving? And really, let's say accelerating, because just to be a little more clear, what would prevent the block from accelerating down the ramp? Okay, so so obviously this thing, it's going to slide down the ramp, assuming there's no friction, and we're not really worried about friction for the time being. So and we know that the thing has a mass of 10 kilograms. So let's put 10 kilograms. Okay, so what is happening to this block right now? Now, the only force acting on it, okay, is the force of gravity. So what I'm going to suggest is let's draw a vector. So let's draw the forces acting on this object. So we have a vector from G to negative to G plus 0 and negative 9.8. Okay, so right there you have a vector which represents what we're going to call the force of gravity. Now the force of gravity pulls the block straight down. Okay? The force of gravity pulls the block straight down. Now obviously not all of that force is simply going to cause the object to slide down the ramp, because some of the force is acting in this direction down the ramp, and some of the force is acting into the ramp. Okay? So the first thing we need to do here is we need to change f of g. So f of g, which is just 10 times 9.8, is 98 newtons straight down, into its components. We need two components. Okay? We need one component which is in the direction of the ramp, i.e. sliding down the surface, and one component which is directly into the ramp and not causing it to slide down the surface. This, by the way, has a special name. It's called Fn, which is the normal force. Okay? So the normal force, so here's the only force acting on this thing is the force of gravity. Now what I'm going to do here, okay, I'm going to draw a second vector that's acting down the ramp, and then a third vector that is the normal. And I know that the two components are an okay substitution because they're going to add up to the same thing. Okay, so again, I'm just going to sketch this roughly, and then we'll get it correctly in a minute. So it has a force going down the ramp, and then it has a force going into the ramp. Okay, if you try and think of it this way. So let's rename this one to call this force down ramp for dr, let's just say. Or, yeah, we could, what does it say? Parallel to the ramp, yeah, whatever. And then let's rename this one to the normal force. So the normal force again is acting completely into the ramp, and is absorbed, right? The force, the dr force, down the ramp force, that's causing the block to slide and accelerate down the ramp. So the first thing to understand here is the force of gravity is equal to the force down the ramp plus the force into the ramp. Right? We know we're allowed to do this because all I'm doing is replacing a vector with two component vectors that I know, of a force down the ramp and a force into the ramp. Now, in this little triangle I drew, right, there's a 90-degree angle right at this corner, and the angle between the angle at point G, right, has to be the same as 60 degrees because force of gravity is parallel to this straight line, and the force down the ramp is parallel to the line that goes down the ramp. So this little angle in the top of my drawing is also 60 degrees, and this little angle in the bottom of my drawing is therefore 30 degrees. Okay? So let's get those angles. You can see I didn't quite draw this perfectly because I didn't get it to be 30, but that's got to be about 30 degrees. That's close enough. And then the angle, the other angle, right? Okay. Oh, right, because I see. So I keep making that mistake. That one, that one, that one. Okay, that's got to be 90 degrees. So let me just see if I can quickly adjust that. Yeah, see this? Okay, so I'm going to have to take, let me take a second and draw it properly. Okay, so just cleaned up my drawing a little bit so we actually have the correct points now. So you can see there's a force pulling it down the ramp and then a force that's acting into the ramp. The little 30 degrees at the bottom would be the same as the 30 degrees over here, and the 60 degrees in the top would be the same as the 60 degrees up there, right? So if you just measure the angle from J to G, you get a 60-degree angle up in there. So the triangle you're drawing is always going to be a similar triangle to the ramp. Now the force that we want to look at, the force down the ramp, well, let's just look at the triangle. It has a 30-degree angle down here. It has a hypotenuse of the force of gravity, and therefore the force we're interested in is simply the opposite of this triangle, right? Just finding the when I say opposite, I mean the opposite as in the opposite side, right? So let's go back here for a sec. I'll copy and paste the diagram. So FDR, the force down the ramp, is equal to the opposite in the force triangle. The force triangle has FG as the hypotenuse and 30 degrees as the angle. Therefore, the force down the ramp is equal to force of gravity times sine 30. And we know that that's equal to 98 times 0.5, which is 49 newtons. Okay, so again, in mine, I scaled it down by a factor of 10. But if you take the length here between vector G and FDR, can it help if I spelled that right? Length. Oh, sorry. That's not G. Sorry, G and J. Okay, it's exactly 4.9, right? And again, because mine's scaled down by a factor of 10. It's I'm working with 9 as if my thing was 1 kilogram, not 10. So let's copy paste the picture so you have it. So you can kind of think of this as the block is sliding down the ramp with a force of 49 newtons down the ramp. So to prevent the object from accelerating, you would need to apply a force of 49 newtons up the ramp. Right? And so that what you're doing there is you're asking, what force would you need to cancel this out so that nothing is acting on the object? Now, the normal force is already canceled out because that's the force that the ramp is exerting on the object, right? That force is into the surface, which isn't causing it to move. It's balanced by a normal force acting from the surface back onto the object. The part of the force that's unaccounted for is this part here, right? The force down the ramp. So you simply calculate that, and then you say, to prevent it from moving, you would just need to apply that same force in the opposite direction. Okay? So if someone was holding this block with 49 newtons of force in the direction of up the ramp, the block would not be experiencing any net force and it would not accelerate. Okay, so if it was stopped, it would stay stopped. Okay? So again, try a couple of these ones. I would say they are much harder to understand than they are to do. So, try to understand them, of course. But, even if you do a couple of them, you'll kind of see, like, yeah, there's not that much to it. You just draw it correctly, make sure you don't mess up which angle you're talking about, and then find this part here. Okay, now, the tricky question is this one. It says a mass of 10 kilograms is suspended by two cords that make angles of 30 and 50 with the ceiling. Find the tension in each cord. Alright, so if we're going to do this, so let's just save this box, and then we'll make a new one. Okay, so for this one, what we have is we have 10 kilograms suspended by two cords that make angles of 30 and 50 with the ceiling. So let's take, let's say one of them is attached over here, and one of them, how do I do this now? Let me just pause this so I can get this drawn. Okay, so your picture should look something like this. Okay, you have a point on the ceiling and another point on the ceiling, and you have both of these points are attached to an object that is suspended. Now, it's a mass of 10 kilograms is suspended by two cords that make angles of 30 and 50 with the ceiling. So that's what I've drawn, right? Sorry, get rid of that. Okay, so here's the part that makes 30 degrees with the ceiling, and here's the part that makes 50 degrees with the ceiling. And the tension, right, is a force that the rope is pulling the object up and to the right with whatever Newton. This tension is pulling the object up and to the left with however many newtons. So this is what your question is, and what you need to do is solve T1 and T2. Okay, so how much tension is in this cord, how much tension is in that cord. Now, to solve this, we're going to apply an idea here. To solve this, let's apply the idea of the net force. So the net force, we said, causes an object to accelerate. A net force causes an object to accelerate. Since this object that we're looking at, since this object is suspended, it's hanging and not moving, right? It is neither moving nor accelerating, so the net force must be 0. Okay? This means that the force of gravity acting on the object must be perfectly cancelled by the tension in the cords. Okay? So now we've got a new idea. I'm going to add a new force, which is the force of gravity. Let's see here. Yeah, I don't really have a... Okay, so vector from point... I think I put the center of that circle at D. Vector D and then to D plus 0, negative 9.8. Okay, so actually, you know what? That's actually not a good idea. Let me my picture kind of makes this look more confusing than it has to be. Okay, so let's imagine the object is located at point C. So maybe I'll just move my circle to point C with a radius of 5. Okay, so there you go, something like that. Okay, so think about the forces acting on this object. One rope is pulling it up and to the right, one rope is pulling it up and to the left, and gravity is pulling it straight down. Now, what do you know about these three forces? What we know about these three forces is that T1 plus T2 plus Fg equals 0. Because the object is not accelerating. So this tension and this tension are canceling out whatever's left in the gravity. Okay? So now that we know this, we know a couple of things, right? We know that the force of gravity is 98 newtons down, right? And so what we need to do is we need to add the three vectors together so that we get 0. To do this, I'm just going to draw them over to the side. I'm not going to draw them exactly, but you can see what I'm going to do. Here's the force of gravity. Then I add tension 1. Then I add tension 2. And I have to get back to where I started. A lot of people look at this and they try to solve this triangle on the top. Don't do that. That triangle on the top doesn't help you. Because it doesn't have anything to do with the forces. Right? Here, oops. Okay, what you want to be doing, let's just take these and just get rid of the names so they're not okay? You want to draw your force of gravity straight down, your T1 after your force of gravity, and your T2 after that. Okay, if once you've done that, now you have the triangle that you can actually solve. Now the trick with this triangle is, of course, what do we actually know about it? Let's write down what we know. We know that this side is 98 newtons. Okay. We also know that we know a little bit about the angles. Now, you got to be careful here because what do we actually know about the angles and where do they go? So here, let's just remind myself what all of these things are. So here's my T2, and here's my T1. Okay, so that's what I know. Now think about what you can see in the picture, right? T2 has an angle of 50 degrees with the horizontal, right? So it's kind of like if I were to draw like a little mini. Sometimes what's helpful in these questions is to draw a little mini axis wherever you're kind of working. Just get rid of G. Okay, if you draw this little miniature axis, you can kind of realize what angles you know and where they are. Okay, so look closely at T2. T2 makes an angle of 50 degrees with the horizontal, so according to my Z pattern, it must make an angle of 50 degrees down here. That means 50 degrees can go, just draw a vector to show, right there, that little spot. And A shouldn't have a label. Okay, and I don't know why J has a label. Okay, so this like the little angle in here would be 50, right? I know this because T2 makes an angle of 50 with the ceiling, so that 50 would Z pattern its way right to there. Now T1, okay, T1 makes an angle of 30 with the ceiling. So the 30, right, would go just right underneath that sort of axis thing that I drew. Okay? So this is sometimes in these questions it's really helpful. Just draw yourself a little axis so that you can kind of make out the acute angles more easily. Another way to do this is, of course, you could approach this angle by doing the same thing. Draw a dashed line across it, and then you know this angle is 30, so this angle is 60. In any case, what we now know, right? So we know that the angle here is 30 and 50, so it makes 80 degrees total. This one up here would have to be 40, because if I were to cut this into a right triangle, then the 50, the 90, and the 40 have to add up. And down here, this has to be 60, because for the same reason. And the whole thing also has to add up to 180, which it now does. So I use this triangle to work out what is T1 and T2. Okay, and all I'm doing here is just the sine law. Always work with the biggest. I don't remember. I'll try and append it afterward. You don't want to be getting into the case where you're doing the ambiguous case of the sine law. So I would say, try to work with the biggest angle that you see. I think that's good advice. I don't know. I gotta refresh myself on that. Anyway, let's go down to this. So it says 98 over sine 80, okay, is equal to, so just using my sine law, so 98 over sine 80 would be T2 over 60, sine 60, equals T2 over sine 60. Okay, and therefore T2 is equal to, T2, right, is equal to 98 times sine 60 divided by sine 80. Okay, and therefore T2 is, what would that be? So let's go 98 times sine 60 divided by sine 80. Okay, so 86.18 newtons. Okay, now T1 divided by sine of, the other number was what, 40? Yep. Sine 40 is equal to 98 over sine 90. Not sine 90, sine 80. And when you solve that one, you get T1 would be 98 times sine 40 over sine 80. Which is 63.96 newtons. Now, how do I know if I did this right? Okay, I'm claiming that one chord has a tension of 86, one chord has a tension of 63.96. I'm going to go back to my vector addition thing. Okay. So let's go ahead and enter the numbers that I think are the answer. So I'm going to say A is A equals 6.396. Okay, that was my value for A. B is 8.618. Okay, so those are my two vectors. Now, what angles are they at? I want them to be sort of opening apart from each other, where one opens with an angle of 30 degrees to the ceiling. So like, here's the ceiling, and I want to back it off 30, so I'm going to bring this down to 60. Okay, my other vector is with 50 degrees to the ceiling, so let's bring it over here, and then we'll bring it up 50, so up to 320. Now, if you look at this, why do I think I'm right? Why should I be very confident that what I just did is right? This tension in this chord acts with 50 degrees towards the ceiling, right? Like my little angle with the horizontal is 50 degrees. And by the way, I did that by making it horizontal and then bringing it up 50, knowing that the Z pattern would be the right thing here. And the same thing with A. I brought it horizontal and then rolled it back 30 degrees. Okay? Now look at the resultant. The resultant is 9.8 straight up. The bearing is 359.997, which is basically 360, right? Yeah, obviously, I rounded a bit in my answers. So if you add T1 plus T2, which is what I'm doing here, you get an answer of 9.8 straight vertical, which is perfect because I want this to cancel the 9.8 that's straight down, right? So I know that my two tensions they cancel each other out left to right, right? A is pulling right, B is pulling left, and that cancels out. And all that's left is that they're both pulling up with 98 newtons. Now again, remember, I had to scale mine down by a factor of 10 so it fits on the applet, but this should be 63, this should be 86, and this should be 98. But again, they all add up to 0. Okay? And that is that means I've done this correctly. So I'm looking at my resultant. I can see my resultant is pointing straight up, and is the right magnitude. So I know I've done this right. So what I'm going to do here for this one, I'll just take a quick picture of this one. This is the check. Again, I think this thing is really handy for checking your work. So maybe try and use it. So here's the check. And then let's do a picture of the original diagram and sort of how we solved it as well. Okay, so again, the tension question, very common. It's probably what you're going to be asked from this section. So solution, and then the check. Okay, so again, try it. I think there's an assignment question on tension. You can give that a try. Remember, the triangle you draw at the beginning is not the triangle you solve. You need to solve the force triangle. The force triangle is start at any point you want, draw the force of gravity, then draw T1, then draw T2, and you must end up where you started because there's no net force acting on the object. When you solve that triangle, you'll know T1 and T2, and again, you can use the applet to check. What you should get as a resultant is a straight up, and it should be, whatever the mass of the object is times 9.8. Okay, so again, feel free to post questions. These ones are tricky; they do take practice, but there's only so many of them. There's only the ramp and the tension question.